Well, hi, I'm Yiyi, and although we have that very general topic here, but given the time constraint, I'm gonna focusing on one of the projects which demonstrate this whole idea. And today we're gonna see how a GM-based neural estimator will gonna do parameter inference for some XID processes. As always, we will start with some brief motivations. So it's important to to monitor the extreme events in all sorts of ways. But of course, the real data can be sparse, skilled, or sometimes even unreliable. And there are a lot of statistical models that tackles this sort of problems and do the modeling, which provide us a very rigorous math foundation for such modeling jobs. The max stable and max ID processes are two popular ones for the spatial extreme modeling specifically. Here are some more specific math formulations for such processes. Basically, two important components are needed. We need a point process R and a random Gaussian process W. But the key components here is this kappa function, which is a mean measure came along with the Poisson point process. Here, for the max ID version, we have a beta parameter and an additional exponential term so that we can include more information from the raw data that we have. In this way, we will have more flexibility in terms of all the tail modeling compared to the original, more commonly used max stable models. More specifically, this beta parameter will control the heaviness of the tails, and the exponential term controls the decay rate of the extremeness in the overall sense. So maybe you're curious that why we not just fit the data into those statistical models and call it a day? Well, the traditional methods not sometimes, most of the times we do this kind of parameter inference for the fitting based on some likelihood functions. And for this type of parameter inference can be quite difficult, is specifically for the max ID process, because the likelihood function is quite ugly and sometimes even unattractable. That's why we need the help with this black box neural networks so that we can go purely data-driven and therefore it has such all the merits which a traditional statistical model cannot share. And more specifically, because the spatial data that we have can naturally be considered as some sort of graphs, which we consider each location as a node and the dependence between all of them as the edges of each graph. And that's why we're thinking about use a graph neural network to do such type of data-driven modeling so that we can do the parameter inference without touching the ugly likelihood math equation. This GM-based method combining with some neural-based estimator is originally proposed by Sainsbury-Dale's paper here. Basically, the spatial dependencies within each graph are going to be learned gradually within this propagation module through some message passing scheme. And the readout module will try to as sufficient as possible to summarize what's been learned in this previous module so that by this step, we can handle all different sort of graph sizes. And after having this readout vector, we can then using some simple mapping functions like the MLPs to transform everything to the parameter space that we are interested in. This neural-based estimator here, they chose to optimize the loss function through some base risk, basically because the base estimator have some desirable properties such as admissible, consistent, etc. But of course, we can consider other different loss functions and estimators to be trained on, considering on different needs specifically. Here is a diagram of the simple workflow that we're going to conduct this whole idea. Basically, we start with some raw observations, can be rainfall, wind speed, whatever, and we're going to wrap them up into some specifically sized graphs. Additionally, we design a classifier which trying to tell us whether the observation graphs are more max ID-like or more max stable-like. By having this information, we will then put all the graphs into either of the inference models so that we can get the final parameter estimations for whichever processes we're akin to. And additionally, we found that if we include more localized information around each node by these features, the model performance will improve a lot. So that we conduct some simulation case study to test our idea. And for the random Gaussian process part, we're going to choose this covariance matrix. And we will train 3 separate neural networks to inference once for each of the process and 1 classifier telling us which way to go. For each of the inference cases, we consider this k number of training samples, and we're going to sample the parameter pairs needed from some uniform parameter space. And this classifier, we're just going to have a 50-50 distribution of the observations coming from each of the processes so that we have a balanced data set and we don't care, like trying to avoid further issues. And first of all, we check the accuracy of our classifiers, and we can see that for most of the beta values, it works pretty fine, have over 95% accuracy of doing a correct identification of the processes. We noticed that when beta is relatively small, the accuracy dropped to around 0.7, which is understandable as when beta closer to 0, the whole max ID process will degrade it to the max stable process, which makes the observation itself becomes more unable to be distinguished. And here are some estimation results for, first of all, the max stable process. So basically, we take 25 randomly sampled truth parameter pairs, which I identified as the orange dots here. For each of the cases, we do 200 independent bootstrap replicates so that we have some sort of uncertainty level for this estimating task. We can see one observation maybe worth noticing is that the variance, the variation of the range for the parameter estimates, especially for this row parameter, is quite large comparing to the size of the parameter space. This kind of situation is handled a little better with adopting a max ID process, but we take a closer look to some cases for the max stable processes, and we found out that large variation situation is actually caused by the identifiability issue for this design of max stable models itself, which in one sentence, it means that for very different parameter pairs, they can produce very similarly distributed observations and causing some confusion in our modeling. And that's another reason why we're trying to shift from this max stable idea to the max ID more generalized version to avoid what's happening here. And finally, we took the model to some real rainfall data. We manually choose 2 regions which have relatively pretty different climate conditions. The classifier told us this Tasmanian highlands will be more max ID-like, and this coastal Queensland part will be more max stable-like. We did the parameter inference use both of the inference networks here, but the key idea here is that for this beta estimation we saw here, they actually agree with the classifier's conclusion, because for max ID, we have a relatively large beta, and for the max stable case, we have a relatively closer to 0 case. Yeah, and that's the whole conclusion also agrees with our initial assumption, where when we choose these 2 different regions based on their climate conditions. And here are some things we're currently trying to do and we're currently doing and will be doing in the future. But that's all from me. And thank you so much.